Good morning, everybody. First thing to say is, at this time in the morning, this is not going to be a lecture by a professor on complexity science. I thought you'd be pleased. The agenda that I want to go through today essentially is illustrated here. First of all, to talk about some definitions. Stephen fought shy of putting up a definition yesterday morning of systems engineering. I'm not going to be so shy. And then I'm going to talk only a little bit about wicked problems to contrast the nature of some of the real-world issues we face compared with some of the ways we actually treat them. In the title of the talk there is the word synthesis, and I want to dwell on that for a moment because I think it's an important word for the future. And then I'm going to dwell for most of the lecture actually on some case studies, because there's nothing like having some of the abstraction that I'm going to talk about well grounded in real experience, and it is my personal real experience in some of the recent roles that you've just heard that I've held. Then I'm going to abstract again some conclusions and then some thoughts for provoking you into asking difficult questions which others will answer. First of all, a bit of history about engineering. Most people don't know that the word engineer comes from a Latin word meaning an ingenious person. And ingenuity is actually, when you look at what engineers achieve, a lot of it is through the exploitation of what ingenuity they might have. And the history of that is that Leonardo da Vinci was the first person to hold that title in Italy. Engineering then became an activity that was codified in France and professionalized in Britain. But interestingly enough, the linkage between engineering and policy in governance has always been quite weak. And I'm actually the first engineering policy professor in the UK. There are a few in the United States, there are a few around the world, but it's a very small club, I've discovered. And yet I will assert as I get towards the end that it's a rather important area for academic work and good practice. So I said I'd put up a definition. I'm going to use yours, the INCOSE definition. And the word that strikes me there is interdisciplinary and successful. There's no point doing it if it isn't successful, and if it isn't interdisciplinary, it's probably not addressing big systems. The other word that I'm going to touch on there is purposeful. If we don't understand the purpose of what it is we're acting upon and doing, then we'll lose track of what it is we're all about. That may sound rather trite, but actually it's all too easy when you get into the bowels of the day-by-day routine of dealing with things to forget why you're doing it. And part of the leadership role, of course, is to keep people's eyes focused on what is the purpose of the activity. And here I must acknowledge the fact that Patrick Godfrey, who you've heard about this morning, and I are working together on quite a number of things, and quite a number of the concepts that I will be bringing out, integrated with my own thoughts, have come from conversations that I've had with Patrick. So Patrick, thank you. Certainly it relates to the development and delivery of goods and services. And services are becoming, at least in our country, more valuable to society than goods. And yet they're more complex because services are things that are consumed in very different ways by people. And I'll come back to the issue of people later. And of course it's got to deliver real benefit. Benefit quite often means numbers that are expressed against some currency. In other words, cash. But actually benefits now are a much broader basket of value propositions. And in the past we have perhaps tried to monify everything into economic or financial terms. Maybe we need a more holistic value proposition set of evaluations for assessment in whether the benefits to suppliers, customers and society are appropriate. And again, I'll come back to that. All technical domains and all business functions. It's quite obvious to all of you that systems engineering has grown out of a subset of business functions and technical domains, but it's now expanding rapidly into lots of other ones. And that expansion process means it needs to be re-engineered in such a way that it is appropriate for the domains in which systems engineering is going to work. It doesn't just fit because it worked in aerospace or in defense. So the re-engineering of systems engineering because systems engineering was engineered, unlike business process. There's this phrase out there called business process re-engineering. When did you come across a business process that was engineered the first time? So I think there is something about how we contemplate our own methodologies and our own approaches and say, are they entirely appropriate for the new domains in which we're trying to apply them? So I'll now move on to systems thinking. Again, a definition. No simple answers. Einstein had a lovely quote that things should be made as simple as possible, but not more so. I think there's a new phrase which you might have heard for the first time here, but I haven't found it anywhere else, which is things should be made as complex as necessary, but not more so. And we tend in some areas to over-complexify, make things over-complex. On the other hand, we shouldn't look for simple answers if there aren't them. And that means looking at the connected wholes rather than the separate parts, and this definition, practical holism, I don't particularly like, but systems thinking is what is becoming quite fashionable. And it is a framework for looking at the interrelationships between things. In fact, some of the work that Patrick and I have been doing is very much deeper than interrelationships. It's interdependency. One piece won't work without the other piece working. And that can be a mixture of things that need to interrelate. It may be people, it may be technology, it may be data, it may be energy, all sorts of things that are interdependent. And those general principles spanning this wide range of fields is crucial. So again, I've quoted from other people's work. Like most of us, we grow on the back and the shoulders of other thinkers who come before us. But what I'm trying to do now is to bring together some of the concepts that others have put forward and describe them in a way which I think offers avenues for exploration and practice for the future. So as an example of systems thinking in national infrastructure, which is where my own work has been and continues to be, and by national infrastructure I mean those boring things like all the transport systems, all the energy systems, all the water systems, the waste systems and the ICT that makes a developed society a developed society. They're boring because you expect them all to work all the time, and we only really notice they don't when they break or fail in some other way. So what we've been looking at in the UK is to see whether there are new ways of thinking about national infrastructure which pull explicitly on interdependency between socio-technical systems and look at ways in which we can analyse and invest in those infrastructural systems in a much more holistic way than we've done in the past. So you don't just build a railway line, you build a means by which people can carry out a journey from A to B. And that's a very different value proposition. In other words, we articulate the purpose from the point of view of the end user rather than from the system's point of view. And therefore you see innovation at the interface between various components of national infrastructure, and you end up with a much more difficult problem of balancing costs, benefits, risks and uncertainties, which needs new tools. You also now need to understand, in a way that probably we didn't 100 years ago, these balancing factors of safety, behaviour, congestion, community impact, noise, air quality, pollution and carbon impact in a way that even 10 years ago you wouldn't have listed all of those. Now anyone investing in this sort of space or any sort of space has to balance all those factors, some of which are you can be analytic about, some you've got to make assessments which are less quantitative. And that means you need good information, and that obviously means you need good data. So data from all sources, over the whole range of the program, what you need in order to decide to do it, what you need in order to build it properly, what you need to operate it. And actually, importantly, in one particular hairy case in the UK of nuclear decommissioning, what happened 50 years ago. Decommissioning is actually quite an important issue for certain areas of investment. So underneath that, the modelling community is now beginning to help us with systemic models that allow predictions to be made right the way through the network and right the way through the life cycle. A little bit about complexity science. As I said, this was not going to be electron complexity science and isn't. And it's still open to debate what the word means. Patrick's university came up with this quote. I couldn't resist having a quote from Bristol University, where Patrick is a professor. And actually, the reason for that is complexity science has grown up in lots of different branches of science. And each has its own particular example of complex systems, and no one's actually found a way of synthesizing the various elements of complexity, although that is now beginning to start. So there is this phenomenon of complexity, emergent properties, instability, uncertainties, but it appears in a variety of systems. And the thesis is that there is a common scientific theory or approach underpinning it, and certainly there are some common mathematics. But when you start applying it in different domains, you end up in different places. But those domains interact and are interdependent with each other, whether it's a social domain, a natural domain, or a physical domain, a man-made physical domain. And that means you end up with the synthesis of complex systems which had already diverged from a common mathematical base, and now you're reintegrating them. So you've got the interaction between complex systems. And we're now beginning to have to understand that, in particular where extreme weather events, which turn out to be very unpredictable. As an anecdotal story, I was in Australia with the chairman of Santos, who are a very large oil company, when the cyclone went ashore in the Bay of Bengal. And he was sitting there with his phone virtually on his head because he got an $800 million refinery right in the track of this cyclone. It missed by 20 miles, but he only knew that 20 minutes before it turned left and missed. Some of you in this country know about tornadoes and hurricanes that come very close or not to wherever you happen to live. So that type of uncertainty, that type of complexity is one we're now having to face in understanding how to build our built environment and how to build the social environment for resilience, evacuating people as appropriate. So those are the examples of what I mean by interacting complex systems and our ability or not to understand how to work in that space. This is a piece of work that a gentleman called Patrick Botemont has done. He's a member of this partnership called the Abaki Partnership, and I put this up with his permission, which is a way of condensing some of what I've said in terms of communities of interest. That's what COI stands for, communities of interest. And I know this might be quite difficult to read because you'll need to twist your head to one side. But on the left-hand side, we've essentially got communities of interest which are really well defined and are the sort of traditional institutionalized groupings where systems design behavior is all verifiable. And you'll all recognize that because in some ways that's the root of where systems engineering has had its most impact. But as you go towards the right, you start seeing groupings, organized response, ad hoc activity, and what is now happening out on the streets, riot mobs and individual activists, slightly topical at the moment. And therefore the methods by which you think about how to address the systems issues that arise in those different natures of communities of interest are written at the bottom. Now, this is derived from a book that Patrick and a co-writer wrote called Complexity Demystified. And it's worthy of a read. It's not a particularly heavy book, and it's written in very open English. So I put that up purely to illustrate the principle that there are various communities of interest with different aspects of how rigid and structured their thinking is about the issues for them. And if you've got them interacting, which in any real situation you certainly have, you need to understand how these different attitudes to complexity, systems thinking, and system engineering actually behaves. Of course, the trick is how do you categorize which one you're in? I'll dwell briefly now on wicked problems. One of the other things I've discovered over my period of working with big problems and big issues is that we try and make them into projects. We try and call them projects because then we can use this discipline called project management to manage them. And we know how to do project management, so it's the old adage, if it isn't a nail, I'll make it look like a nail because it's a hammer I've got. And I think wicked problems are much more descriptive of the real world, and we need a new structure by which we lead and manage the strategies for developing the solutions to wicked problems, which are typified by the fact that you don't really understand what it is you have as a problem until you start trying to solve it. So you learn by doing. And if you don't learn by doing, you continue to make the same mistakes time and time again. I'm sure that'll ring true with one or two people in the room. Wicked problems tend not to have a beginning and an end, unlike this thing we call a project, where we know when it starts and we know when it ends, because that's what the project management handbook said. Actually, the real world isn't like that. It doesn't have a clear start and it doesn't have a clear end, because we've always got the legacy and we've always got the things beyond what it is we thought we were stopping with. And there aren't right or wrong answers. Everything usually is a new one. We haven't done it before, because whatever it is, it's different from what we've done before, because what we've done before affects what we're doing now. And it therefore is a one-shot operation. And what's more, once we've started doing it, it's very difficult to find alternatives, because it does lock you into all the things you're already doing. So I'm not going to dwell any longer on this. There's a body of literature, both in professional practice and in the academic world, about wicked problems, but I would espouse the idea that it is something that gains a little more traction in the way in which, especially to the right-hand side of the diagram I put up earlier, where things are less well defined, methods by which wicked problem solutions are used as opposed to project management. I'm not throwing out project management, I'm sure you'll understand that. I'm just saying you need a toolkit which is fit for purpose. And then finally, before I come to my case studies, the issue of synthesis. The academic literature, and indeed a lot of professional practice, is dominated by the word analysis. In other words, we break it out into smaller and smaller components, and once we got it down small enough, it's tractable, and then we solve it. What we don't understand how to do is put it all back together, partly because synthesis is a harder word to say than analysis. But have anyone in the room got a job title with the word synthesist in it? No? Anyone got the word analyst in their job title? None of those either. Well, that's interesting, isn't it? So you'd either don't break it up or you don't put it together. But you see what I'm getting at, I hope. But the idea that joining things up needs a new discipline of work. And of course, that is something that is beginning to happen, partly through modelling and partly through new ways of thinking about the mathematics of synthesis. And indeed, the award for the paper from MIT this morning was exactly in that space, as we know your work and you know some of our work. So it tends, however, to be observational and principled. And that's good, because you need that sort of work. But taking it out and making it pragmatic and practical is not something that's really happened very much as yet, except in case studies. So there is a lot of case study material of how it's done by people who have an intuitive grasp of how to do it. But that makes it much more difficult to teach. And that means you need experiential learning. And experiential learning, embedded in the way in which you go about synthesizing large, complex issues, is where I think a lot of the action will be, and it's where Patrick and I also are working. Partly to do them at scale and partly to do them reproducibly. So, my first case study. First case study was the modernisation of a railway line that goes north-south through London. And it's called Thameslink, and it was a modernisation programme that was going to cost £3.5 billion. I'll just throw up a map so that those of you who are unfamiliar with UK geography. On the left there is London. So that's the pinch point. So there's lines coming from the north and the south. There happens to be airports at on both the north and south lines. So not only are we going through the middle of London, this pinch point here, we've got airports up here and an airport down here somewhere. So we've got a loss of traffic, both commuting and tourist and international traffic on these train lines. And they all go through this bit in the middle, which is the main north-south artery through London. So the thesis was that in order to make this better, we need to increase the passenger throughput. Absolutely crucial to the business case was to get a lot more passengers, particularly through that middle bit, particularly at peak hours. London, about 2.5 million people commute in and out of London every day. It's an 8.5 million, pushing 10 million city, so we're investing in this for the future. So what we immediately realised, I immediately realised, some of my colleagues who were in the programme didn't because they'd forgotten the purpose, was that the behaviour of people getting on and off the trains who paid the fares, which was critical to the revenue, and of course the revenue piece is the value proposition, that's the benefit in the cost-benefit equation. And that, unless you got enough passengers on and off the trains, you weren't going to make a viable business case. The model that they were using to look at the behaviour of people getting on and off trains was based on a 30-year-old design of old types of rolling stock and very, very simplistic analytics. So when I looked at the numbers, my intuition told me they were wrong by at least an order of magnitude, if not more, and that's an order of magnitude in the revenue. And that sort of rather destroys the business case. So eventually we managed to get them to understand that they needed to use what had already been created, a new experimental rig, which looks at detailed observations of how people get on and off trains. Now that may sound a very simple thing from a systems engineering point of view to model, but actually it isn't. It's hugely difficult because you've got a very wide variety of people carrying things with children, with buggies, with luggage, infirm, elderly, just bloody minded. And so we never have that in the US, do we? We don't have people who travel like that. So the issue of how people got on and off trains was something we actually then did a whole raft of experiments on. And that transformed the way in which carriages, platforms, furniture and timetables were designed. And we got the whole thing back roughly in a place where it was usable. So the assertion is therefore that the trust in models without making an analysis of examination of the assumptions and listening to your own intuition is a very dangerous situation. And that is now having an impact on Crossrail and very large programs, the largest civil engineering project in Europe. It had an impact on our Olympics and other legacy system upgrades in our high-speed rail link. And it is now taking a view outside or onto the interdependence between transport projects. This is the facility. It happens to be at my own university, but that's accidental. And you can see here's the rig of a train. We're actually instrumenting a bus as well, because buses accelerate and decelerate, especially electric buses. The torque you can get from an electric motor allows a bus to accelerate at a much greater rate than you can with a diesel engine. But of course passengers don't know that. They just get slung to the back as it takes off. And the drivers aren't trained to control it at the moment. Well, we're working on that. So this is down the bottom is an aerial view of the way in which we analyse how people move. Everyone's labelled. We have masses of cameras, lots of video analysis, lots of other forms of analysis. And it's called Pamela, and we'd be delighted to talk to anyone who might want to come and work with us on their problem. Case study 2, different, totally different, biomass. The exploitation of biomass to make biofuels. What was the case was that cultivated and natural biomass can be used for fuel. Brazil had been doing it for 30 years, seemed a really good idea to develop low-carbon fuels by the use of biomass. However, it was then noted that if you grew this at any sort of quantity, then you grew that instead of food, and if you grew it instead of food in poor parts of the world, you starved people. So we can have low-carbon fuel, they don't have any food. Not a particularly good ethical position to adopt as a Western country. And what's more, we discovered that actually a better way of using biomass was for energy and heat rather than fuel. So what we needed to do was understand how to make biomass feedstock sustainable and possibly mix it with commercial and domestic waste instead, obviating the need for a crop-based approach. What we also discovered was that when you start growing crops in soil that has never been cultivated, you have no idea how much carbon is released. I'll show you some curves in a moment. So the uncertainty around this situation of the science and the engineering and the ethics was huge. And yet, the UK and Europe had already committed itself to biofuel targets, which caused us to go into a position which was unethical, unsustainable, and going to be very difficult to get out of. And what I did with colleagues was to create a pan-departmental science and policy coordination activity, which generated a lot better evidence and allowed our politicians to get in a sensible place. And it changed the UK policy, it changed the legal structures, but our politicians didn't lose political capital. And that's a very important issue, because without that, we would have been in a really difficult international situation. The other thing I'm pleased about this piece of work is it is the subject of an academic paper. I write academic papers, but this is the first time I've ever been the subject of one, because someone looked at the role that I and a colleague held in brokering this type of activity. And as a result, we're now in a much better position to enable national and international trust in sustainability of feedstock. It's interesting it goes in cycles. I've watched the press and this subject, which I'm not working on particularly at the moment, has just come back into visibility again. Just to put a little bit of flesh on it, this is the sort of life cycle of a biofuel process, and it's this stuff, it's the feedstock that is the issue. After that, it's fairly straightforward. It goes straight into relatively standard refining processes. But if you get that bit wrong, then you've really made life difficult. And I mentioned the issue of not knowing what the carbon emissions were. Here is the gram of carbon dioxide produced per megajoule of energy for different crops, and you'll see the coloured bars are the same crop but grown in different parts of the world. And at the bottom you can see diesel, gasoline and coal to compare it with, and you can see particularly here where you've got sugarcane in Brazil and Mozambique, where if it's grown there, it is a lot better than than diesel or gasoline. But if you grow it in South Africa and Pakistan, where they haven't tilled the soil before, you release so much carbon that it's actually worse. And that's the sort of uncertainty that made the science, and hence the policy frameworks, completely unsustainable. Third case study, again very different. Volcanic ash and civil aviation. This was a volcano called Eyjafjallajökull. Now, there will be some Scandinavians in the room who will know that isn't the right pronunciation. But it's close. And it was known as that volcano in the UK during the saga. And some of you, and in fact probably most of you, were impacted by that particular episode, and you will be horrified to know I was in one of the hot seats at the time for the 5 days that we had to deal with it. It had not occurred previously. In the previous 30 years, we hadn't had that type of eruption through an ice cap, and that was what was distinctive about it during that period. Therefore, because it hadn't happened, there'd been no specific science or engineering investigations on that type of volcanic ash. And the regulation all around the world was, don't fly through ash you can see, which is pretty obvious, but actually what that said was all volcanoes that erupted prior to that had produced such large density of high mass particles that you could see it very easily. And it had two effects. One, you could see very clearly where the edges were, and secondly, it fell to ground relatively near the volcano, so it wasn't too difficult to avoid. This stuff, unfortunately, not only was it very small particles that went through an ice cap, and because it exploded, it went up very high, the combination of prevailing winds, the fact that in the 30 years since the last volcano we had grown civil aviation in Europe by about a factor of 100, it was Easter vacation, and this ice cap eruption, that meant high altitude, persistent, very fine silicate ash, which you couldn't see. You could detect it with LiDAR, you could detect it with satellite observations, and with the right radar frequencies you could see it as well, but you couldn't see it with the naked eye. And we had real problems with some of the airline directors, chief executives, who said, but the regulation says I can fly in it if I can't see it. And of course we started to say, yeah, but see means detect, doesn't it? And one particular Irish gentleman said, no, it means see. You probably know what I'm talking about. So we had 5 days of really frenetic activity with huge political pressure. We were costing Europe best part of £2.5 billion a day by closing airspace, just Europe, what we were doing to the rest of the world, of course, because aircraft couldn't get into Europe or out of Europe, to open that airspace immediately. But what we needed to know was two things, and this is one of the subtleties. Not only did we need to know the density, we needed to know the duration, because actually this is an accumulation problem. It's not just the actual density, it's how much ash you accumulate in your air intakes as it goes through the engine. And it took us 5 days with conference calls all around the world, 7 or 8 times a day, with hundreds of participants, everyone being incredibly disciplined, right from the systems engineering end of people who understood how jet engines work, to politicians and financiers and regulators and insurance brokers, you name it, everyone was sitting around with an interest in it. But the important message I want to leave with you is that we could do that because we had already made the investment in the science and engineering base in industry and academia right around the world so that we could immediately pull together the people to do it. We didn't know that was going to be the wicked problem we had to solve, but we did have the capacity and capability, and obviously because of the circumstances we had the will to actually make this problem fixable. That's the volcano before it erupted. That's the ice cap on top of it. That's what it looked like as it was going off. Well, after the worst of it, of course, because we couldn't get near it. And this, just in case you've never seen these sorts of maps, this shows the persistence of the ash cloud over Europe. It went all the way across into Russia, down across Europe, right the way across to the eastern seaboard. Why? Because it went up so high and then got stuck in circulating currents, and it stayed there for weeks. It slowly degraded in density, but we were monitoring it all the time to make it better. So, and it wasn't just the engines, it actually abrades the wings, it clogs up pitot tubes so that you don't get decent airspeed measurements, it abrades landing lights, it abrades antennae, really quite dangerous stuff, but what it does to an engine is deposit itself as glass in the back end of the engine after it's been heated and cooled, which transforms the nature of the engine efficiency dramatically, indeed in two ways. One is slow degradation, the other is due to clogging up of intakes, catastrophic failure. And we weren't going to go anywhere near having an engine fail on us, because obviously if one went, they all went on any given aircraft, because the dosage, as it were, would be pretty well the same across the whole aircraft. So again, it's an example of where we played in the systems engineering as described somewhat in this diagram, right the way through to the politics and the economics. And we used all the techniques that we had available going back to that diagram of communities of interest to play all those factors off against each other. And that's why I think what we need to do is understand how to codify these sorts of things in such a way that we can understand the methods and approaches that are needed in order to deal not just with catastrophes like this, but with normal processes in the way in which we build our complex systems. So going back to some abstraction, therefore, the real world issue is how we synthesize the problems and interests of communities of interest during the whole life cycle of an activity. This was a very short activity in an emergency. But if you've got a planned activity of some sort, then understanding what toolset to use at what stage is what I'm asserting is a necessary thing for systems engineers and other engineers and other people to understand how to do. But if you use the wrong one, then it's a recipe for failure. The real trick, therefore, is to understand what type of community of interest it is you're dealing with. Is it at the left-hand end or the right-hand end of the spectrum of possibilities? And therefore, the governance of that becomes an issue. Patrick very kindly invited me to a seminar, and this YouTube clip, which somehow you'll get hold of these slides, that YouTube clip is another half-hour lecture I gave on the governance of integration, which tries to unpick some of the issues that one might need. Obviously not time to do that now. But it also means we need new metrics for success, and they've got to be value-based because you can't quantify everything. So not only do we need new metrics for success, but we also need hybrid ways of mixing competition and collaboration, because it's not clear that competition, which delivers market efficiency, actually is the most efficient, most effective way of delivering effective outcomes when people are carrying different shapes and sizes of risks and benefits and opportunities. So somehow we need to rebalance the mixture of competition and collaboration in different phases as we go through the life cycle of an activity. So just to conclude, and then I'll give you some questions for provocation for questions. This, I think, is one of the big questions that we need to understand how to answer. I'm not saying I know how to answer this. This is, because I'm an academic, the sort of question we put to teams of academics to say, let's think about research proposals to understand how to do this. It's co-evolution of solutions to problems. It delivers mutual value-based benefits and, importantly, enables embedded learning so that as you go forward, you understand what you have learned from the benefits and mistakes that you have made, so that that can be passed on in teaching and that can be managed for the future. The second thing is actually we need concepts of governance. I've touched on that somewhat already just now. But without that, we will not deliver the synthesized world that works efficiently and effectively. We'll be continually doing and reinforcing our siloed behavior, which is probably inappropriate. And in order to do that, I think we need standards, good practice, and innovation that co-develop. We need how policy and practice learn from each other. One of the theses of the new department that was mentioned earlier, that I'm now heading up, which is only just starting, is how to impact policymakers with good systems and systems thinking, but it's also how policymakers can impact how systems thinkers communicate about what they know and don't know. So it's learn from each other, a discourse. That all forms of capital value that invested are valued. We tend to think of politicians over there and we'll deal with them later. And that's one of the things that you really make a big mistake. Political capital is a crucial investment in what we do, and they are part of the system. If they're not, they're part of the problem. They've really got to be part of the solution. So having that discourse early with politicians so that their political capital can be well placed at an appropriate level of risk and benefit for them is a very important part of the thinking that we're putting forward in our work. And that, as I said earlier, competitive and collaborative practices can coexist. Now, there's a certain cartoon strip which I always think has the last word on these things, so I thought I'd pick on 3 of them. Firstly, on metrics and data. This actually says put the political capital in early. Right, well, I thought that one would ring a chord. I think you might like this one, my assertions about project management and planning. But it is actually a serious note at the end that if you do call it the purpose, then the plan becomes a means by which you achieve it, not an end in itself. And lastly, and most importantly in some ways for me, benchmarking, which I think is one of those other areas where it has some value, but it also has some... But it also touches on this issue of maturity and what a community of interest has by way of its properties, because if it isn't mature enough to handle the complexity that it is trying to address, then it will almost automatically fail. And I think there is an issue to do with how we evaluate the maturity of elements of organizations and their ability to handle complex issues. So, some questions I hope that might stimulate some debate. We have an issue to do with the way in which we're putting ICT and smart technologies into almost everything we think about. And that means data and information is available very much more quickly than we'd had it before. 3, 4, 5 orders of magnitude more quickly. But political timescales and political life cycles haven't changed a jot. Now, any control systems engineer will say, well, if the political system control loop is part of the system and we've just changed the time constants everywhere else, it's going to go unstable, right? And I think what we're seeing is certain elements of what we're doing going unstable because we haven't understood this mismatch between time constants, fundamental sort of clock rates, tick rates, of various elements of this complex society we built. Data governance and data acquisition in this multifactorial world is tricky. Comes into this issue of privacy at one end. There's a scale of data, there's a thing called big data, open data, which is a very hot political issue in the UK at the moment, and I know is here too. And indeed G8 made a big statement about it only last week, which I thought was interesting, and I know the UK was one of the major drivers for getting that out there. Most of you will recognise this. Our university, my university, and indeed I know Patrick's university in the UK, is pushing hard to make sure that we deliver engineers. We can't do much about the politicians yet, but we're talking to the people who educate politicians to break out of this siloed behaviour, because whilst you need domain experts, I'm not decrying that at all, we also need people who understand the big picture and can work in the big picture. And I think INCOSE and systems engineers can take a lead in establishing this new world order, and I don't mean that in the old sense, in a new sense. By producing thought leadership events, by convening mechanisms for debate about this subject, on multidisciplinary discourse, methods education, principles for governance, the superstructure that allows systems engineering to have appropriate and proportionate impact where it should do. And I think INCOSE is on a very good track to deliver on that, and I would be very happy to engage further and see if I can help with any of that. Thank you very much for your attention.
Thank you very much. Fascinating. We have time for questions. So we have microphones placed same place they were yesterday morning. If you want to ask Professor Collins a question, please step up and I'll take them. Please.
Hi, I'm Charlotte. Is it on?
Yes, it is.
I'm Charlotte Papageorge from Orbital Sciences. And maybe I missed this, but in case study 2, you said you came up with the solutions so that you didn't starve the poor people. And you had the graph, but I didn't know what country and what fuel you decided to go with.
It wasn't as simple as that, as you might have expected. What we put in place was an obligation on people who used feedstock in their biorefineries to say where it had come from and why the mechanisms by which they got it caused more food or more land to be used for food than they had displaced by growing the feedstock. And that was a legal obligation. So they couldn't just go and buy it from some part of the world, and it was Indonesia was the one that was the most topical. And to some extent still is, which is why it's just come back. The smoke that's pouring over Singapore and Malaysia has come from clearing forests in Indonesia, and there is an assertion that it's going to be growing palm oil for biofuel. So there wasn't one country and there wasn't one crop. What we put in place was a process to make sure the feedstock delivery processes were sustainable from wherever it came. And that obligation certainly caused a certain amount of tension in the companies who were doing biorefining, but they started to realize their brand value was going to be shot to pieces if what they were seen to be doing was starving poor people in developing countries, and they then complied pretty easily and quickly. Does that help?
Yes, ma'am.
I have a question about your case 3, basically that volcano.
Oh, go on, try.
No way. You said you already had an already convened or made investment to create a network of I guess, SMEs, experts, to answer problems. Was that brought together? And I mean, how long did it take to bring that together? And did you train, have, lack of a better term, conference room pilots like you would in disaster recovery to get up and running with that?
Okay, so somewhere around 36 hours to find the right people. In my role as a chief scientific advisor, I should explain, there's one in each department of state. And because this was a transport issue, it was sort of fairly high up my list of urgencies. And my role was to make sure I knew where people were who had various domains of domains of expertise in the areas that were relevant. So I knew the chief engineer of Rolls-Royce, and when something went wrong like this, I could ring them up. I knew where the aerospace research work was done, happened to be at the university I used to be a professor at, Cranfield. So I knew the people there. I also knew where the atmospheric science research was being done, which universities funded it, who had the modelling. Now, other colleagues in other departments knew where the geologists were, the volcanologists were. So our network of CSAs could immediately multiply out to 10 or 20 domain experts. And once we pulled all them together, and everyone knew this was urgent and necessary, and then absolutely brilliantly, we discovered a young lady who was working in our British Geological Survey who had done a PhD thesis on that volcano. So she knew it intimately, if you can know a volcano intimately. And so she was brilliant because she knew everything about the type of minerals that were in it, the geology, what the likely makeup of the particles were going to be, and what that would do to the aero engine. So within 36 hours. Now that said, there is an established process for emergency management in the UK government. So the process was already there. What we needed to populate it with was SMEs, SMEs as you call them, subject matter experts, with the leadership of, actually in this case, the government chief scientific advisor. And we met daily, and in 5 days did the science bit, and that was called a scientific advisory group. There was another group that was run by the Civil Aviation Authority, which was the regulator for safe aviation, that was working globally to establish what the airlines and aircraft manufacturers and engine manufacturers all over the world thought was an acceptable strategy for developing a safety case for flying in this stuff. So there was another layer of regulatory stuff going on, and that is a well-oiled process as well for different reasons, not because of volcanoes, but because there are emergencies in aviation at all times, and they need to be able to put that together fast. So there were two sets of processes that could be switched on very quickly and populated with domain experts very quickly as well. And that has now become much better institutionalized, unfortunately, because we don't like these sorts of things, for almost anything that happens.
Yes, sir.
Mike Henshaw from the UK. I want to talk about the same case study and just ask you a question about that as well, actually. What you've described is the process, the scientific and engineering process that you went through to get answers. And you've described some of the interactions with the airline directors and that sort of thing.
Yeah.
One aspect that you haven't touched on, but I think probably was quite significant, was the way that the media dealt with the problem. Along with probably every other academic in the UK who'd done anything to do with aeroplanes, we were inundated with the press calls asking us for opinions of whether it was safe, whether it wasn't safe. But in a dynamic situation like where things are happening very fast like that, actually the prevalent attitudes and the way that people behave can be very significantly influenced by the media. I don't know whether that was taken into account or how you dealt with that, and whether that's a significant problem for other similar sorts of events.
Good question, because the media, I said about politicians, should be considered to be part of the system of systems that you need to evaluate in circumstances where you're dealing with issues. And it is also true that the media should be. And it's very difficult to do that because the media have a different business proposition. They want to sell stories, and stories tend to sell better if they're off the edge of normality. We had enough edge off normality with this anyway, but to further excite it and exacerbate it on the fact of speculation and not be very clear that it was speculation. So there was some mischievous reporting. There was some hearing the lobbying of the business community and the airline community over the top of the people who were actually trying to deliver the engineering and scientific evidence that should have been and indeed was. So resisting, used at the end, so resisting that sort of situation was very important. It was clear that this particular incident was actually handled at a very senior level in the UK government. So most of the high-level communications was I didn't see. I had my head down dealing with what I was dealing with, and if that wasn't my job to do the communications of it. We obviously fed what we knew and what we didn't know and what we were doing to deal with what we didn't know to the communications people, and those messages were sent into the media process. To what extent they chose to listen, be partial in the way they use that evidence, it's always outside your control, and that is what communications experts are about, is making sure it's very difficult for the media to be partial in the way they use the evidence. But there certainly was in that case partial use of evidence which excited various communities to go in certain directions. And we learned from that. So in subsequent incidents, we're getting better at trying to wrap the evidence up in such a way that it can't be deconstructed to be used in a partial way, but it's not always possible. So it's work in progress, that one. We didn't necessarily get it right, but I don't think it was too bad once the facts actually came out. No aircraft dropped out of the sky, which is really what our worry was.
This will have to be the last question. Yes, sir.
Thank you. My name is Tim Christopherson. I'm with Raytheon. First a comment and then a question. I think that the solution for a wicked problem may have been demonstrated yesterday in Miami, where the Heat had their celebratory parade, and no backpacks were allowed for the audience as a result of the bombing. Excuse me? I'm sorry. Thank you. Let me start again. Some people couldn't hear. I have a comment on perhaps the solution for a wicked problem was demonstrated yesterday in Miami at the celebratory parade for the Miami Heat, who just won the NBA. And there were no backpacks allowed. Does that jive with you for a solution to a one-off kind of problem? Because obviously what they would want to do as a response to the bombing in London, that is in Boston, excuse me. My question is, though, that I had read a newspaper article recently about that volcano, and it suggested that the carbon emissions had eliminated any of the savings that we had made over the past number of years, and I don't recall. It was a significant number. Are you familiar with the study, and could you provide any comments to it? Thank you. Okay,
the first point, terrorists are imaginative people. Telling them to take off backpacks, all they'll do is produce some other way of attacking the situation. I'm not saying it's the wrong thing to do, but I wouldn't fall into any sense of false security that is actually going to stop some determined person blowing themselves and the situation up with some other packaging of devices, which are already seen anywhere else in the world anyway. So it's a panacea, and I think. And it's good for the media, it's good for the public, it's good for confidence building, but in any technical sense, I wouldn't go too far. I am aware of that story of the impact on carbon. I've never seen the analysis at a level of detail that would allow me to say I agreed with it, but I was aware of the story. I mean, it's a nice, neat thing to be able to say, but. All these carbon emission structures, particularly for aviation, are really complex. And I don't know that we've really got to the bottom of all of that yet anyway. So I think, again, that's a drop in the ocean of what is actually going on day by day around the world.
Thank you.